Okay, we got a lot to cover tonight. I'm going to go ahead and start on our next section here. And we already talked a lot about ohms and everything like that, but now we're going to get into more details about resistors and Ohm's law. Okay, power is a term that describes the rate at which electrical energy is used. And previously, we talked about voltages and current. Well, it just so happens that power is measured as a function of both current and voltage. But before I get to that, what you do need to know is electrical power is measured in watts. You'll often hear terminology also, like it's very common to refer to something in terms of kilowatts or even megawatts. And once again,
Hey,
if
Joe,
everybody
excuse me.
make sure that
Someone's
you're on.
mic is hot again.
Yeah, yeah. If everybody could go on mute, please. Thank you so much. Okay. The formula
Yeah,
used
sorry
to
about that.
calculate electric power in a DC circuit is equals voltage multiplied by current. So over here, power is equal to voltage times current. And over here, this is a very common methodology to sort of remember how these formulas work. It's the pi diagram. You've got P over I times E. So if you ever wanted to know what the formula was for these, what you do, and they'll show this in subsequent slides, is you just cover the value that you want to calculate. So if I wanted to measure, for instance, power, if I put my thumb over the P in this diagram, the equation is I times E. The power being used in a circuit when when the applied voltage is 13.8 volts DC and the current is 10 amperes is, anybody want to take a gander at that? Although the equation's down here. Yeah. So for solving for P, like I talked about before, what you do is you'd cover up the P with your thumb. E is 13.8 volts and I is 10 amperes. So 10 times 13.8 would be 138. And this is exactly a question that you might see on the test. The power being used in a circuit when the applied voltage is 12 volts and the current is 2.5 is, okay, so now E is 12 volts, I is 2.5. The formula is 2.5 times 12, which will give you 30 watts. And the amount of current flowing in a circuit when the power in a circuit is 120 watts and the applied voltage is. So in this particular case, now we're going to cover up the lower left-hand corner of the pi circle, and the formula is P divided by E. So I equals P over E, or 120 divided by 12, or 10 amperes. The formulas used to calculate voltage in a circuit. Hold on a second. Let me reread this again because I think there's actually a typo in this slide. This formula used to calculate voltage in a circuit, voltage equals current multiplied by resistance. So earlier we were looking at the pi diagram and that had P over IE. Now we have another one here that has E over IR. And you can use it the same way. Voltage is equal to current times the resistance, or E equals IR. And again, this is kind of a depiction of one way that you can use this information in the form of a circuit. This is from the previous lesson we had here. Over here, if you wanted to know what the voltage was across here before you even read the voltmeter, you could calculate it a different way. If you cover up the E and you knew what the current was, and this resistor here they're saying is 3 ohms, you would know that the voltage across there is whatever the current is times 3. So if the current was an amp across a 3 ohm resistance, it would be 3 times 1, or 3 volts. So the voltage across a 2 ohm resistor, if a current of 0.5 amperes flows through it, is, okay, we're going to cover up the E, the formula is IR, it equals 0.5 times 2, or 1 volt. The voltage across a 10 ohm resistor with a current of 1 ampere is, again, V equals IR, 1 amp times 10, or I should say 1 amp times 10 ohms equals 10 volts. And I'll do one more of these, Nelson, and I'll tell you what, I'll let you jump in for a little bit if that's okay.
That's fine, sure.
The voltage across a 10 ohm resistor, if a current of 2 amperes flows through it, is 2 amperes times 10 ohms is going to equal 20 volts. And by the way, everybody, as usual, these are all test questions here. So if this concept is making sense to you, here is a bunch of questions that you should be able to work through fairly easily on the test. But no kidding, that is a verbatim test question out of the technician test pool. They'll ask you, hey, you got a voltage across a 10 ohm resistor with a current of 2 amps. How do you calculate it? And as long as you get comfortable with the pi circle and the E over IR one, you'll be able to do all these. Okay, Nelson, you're up next.
Okay. All right. So parallel circuits. You look up the upper right there, there's 3 resistors, and they're connected in what we call parallel, meaning they're connected on the same side to one wire, and on the other sides, they all connect to the other wire. And the current divides between these different paths. So the same formula still works, E equals IR. So if you know the voltage in this case, because you know what the battery is, and you know what the resistors values are because they're given to you, or you measured it with a meter, then you can calculate the current through each resistor. And the currents will sum. So if you look at the current flowing between points 1 and 2, it'll be the sum of the currents flowing across all 3 resistors, okay? So we'll talk a little more about that. But again, the current that's coming from the battery along the top wire 1, 2 is going to divide across these 3 resistors. But of course, Ohm's law will work in all cases. Okay, go ahead, Joe.
Okay. Oh, and that's just another depiction of that circuit there.
Yeah, okay, thank you. Okay. So a current flowing through a 24 ohm resistor connected to 240 volts is the current. Now, in this case, we're calculating the current given the voltage in the resistor. So the current is 240 divided by 24, or 10 amps, okay? So you can calculate the current if you're given the voltage and the resistance. And again, this is not the pie chart here, but it's similar to the pie chart the way it's depicted, with the E on the top and the I and the R below, okay? Okay, next slide, Joe.
Yeah.
Okay. The current flowing through an 80 ohm resistor connected across to 120 volts is, okay, again, you take the voltage, E, or the electromotive force, 120 volts, and you divide it by the resistance, 80 ohms, and you get 1.5 amps, okay? Next slide. Okay, similarly, the current flowing through a 100 ohm resistor connected across 200 volts, again, voltage E, 200 volts divided by resistance R, 100 ohms, 200 divided by 100, 2 amps. Okay, now at the bottom right here, we have a series circuit. Suppose you take resistors 1, 2, and 3, and you put them all in series as opposed to parallel, okay? What happens? Well, in this case, it's kind of simpler to understand, I would say. The resistors just add. So the total resistance is the sum of the 3 resistances. And then Ohm's law still applies. Ohm's law applies for the entire circuit, how much current will flow out of the battery. But for each individual resistor, Ohm's law also applies. What's the current through the resistor? What's the voltage across it? And then E equals IR still works on that individual resistor. Okay, next slide.
So I have a question on that slide for a second.
Yeah.
So is the the current that you're measuring cumulative? So in other words, if you were to measure it after the third resistor, you would have to calculate it for each of them?
Okay, that's a good question. Okay, here's a fundamental law of physics. Electrons are conserved. Okay, the electrons are negative. They're going to flow around this wire. They flow from negative side to the positive side because they're negative. So there has to be as many electrons flowing through resistor 1 as there are flowing through resistor 2, as there are flowing through resistor 3, meaning the current in all three resistors has to be the same. There's no split anywhere in the circuit where the current could diverge, if you will, to another resistor that's in parallel somewhere or some other circuit. So the current is the same all the way around this three resistors and battery, and that's because electrons are conserved. Okay, so does that answer your question?
So I guess you're saying that regardless at what point on that diagram you measure for current, it's going to be 2 amps.
That is
It
correct.
won't be 6 if you're at the end, or 2 or 4. It'll always be 2 amps.
It'll always be 2 amps because the electrons just flow in the wire or flow through the device. It's like water in a pipe. Okay, you put pipes, a bunch of pipes in series, and some pipes are 1 inch, some are half an inch, some are quarter of an inch. You put water through there, and then you say how much water is flowing through each pipe, per minute. If there's 2 gallons per minute coming out the quarter inch pipe at the end, there's also 2 gallons per minute flowing through the 1 inch pipe or the half inch pipe or any other size you have, right? And the different sizes of pipe will tend to resist the water flow more or less depending on the size. Okay.
So what would be the purpose of having 3 resistors like that? Is it to achieve a certain amperage at a certain point? Like, I don't understand what would be the purpose of that type of circuit then.
Why do you care about 3 resistors in series? Yeah. Okay. Well, yeah, that's a good question. Actually, there might be a practical example of using this. Is suppose I have a bunch of resistors in my junk box, okay, and I have a 1 ohm resistor and a 5 ohm resistor, but I want to draw the amount of current drawn by a 6 ohm resistor, okay, but I don't have one. Well, I can take the 5 ohm resistor and the 1 ohm resistor, put them in series, and that makes a 6 ohm resistor. And now I'll get what I'm trying to make happen. I'll get the current that goes through a 6 ohm resistor.
Oh, but I thought you said they're not cumulative, though. That's what I was asking.
The resistance is cumulative.
Okay, because my experience with them is with making speakers. So I have like a 2 ohm speaker, a 4 ohm speaker, but my amp is only able to use 8 ohm speakers. So I would put a resistor in front of it to increase the resistance at the speaker so you don't blow up your amp.
Right. And indeed, the resistance adds. So you're taking your 2 ohm speaker, you're putting, I don't know, maybe you put 2 of them in series and then you put 2 ohm resistors in series in addition. Is that what you did maybe? But anyway, you increase the total resistance by putting speakers and actual physical resistors in series, correct?
Okay, I understand now. The amps stay the same, but the resistance changes.
Absolutely, you got it. Good, very good question. Any other questions about this issue of series and resistance adding, but current being conserved?
Mm-hmm.
No. Okay, very good. Current, by the way, is conserved in more complex circuits as well, but you may have cases where the current divides between parts of the circuit. Okay. This formula here is used to calculate resistance. So if you know the voltage E, and again, the way I remember that is electromotive force for E, and you know the current I, then you can calculate R. Okay. So if you have a battery and you have an amp meter, you can calculate R for the circuit. Okay. Next slide, please. Okay, so suppose you have a circuit with a current flow of 3 amperes and you have 90 volts coming out of a power supply of some sort, either a battery or some other power supply. What's the resistor? Well, it's the voltage E divided by the current, which is 3 amperes. So it's 30 ohms. So 90 divided by 3, 30 ohms. Okay, next slide. And the resistance of a circuit in which the applied voltage is 12 volts and the current flow is 1.5 amperes. Again, voltage E divided by current I. 12 divided by 1.5. You have an 8 ohm resistance there. Okay, next slide. Now, the resistance of a circuit that draws 4 amps from a 12 volt source, 12 divided by 4, 3. You have a 3 ohm resistance. Now, these I assume are questions that are typical in the tech exam. So, if you remember, E equals IR, and you know how that little equation can be manipulated to calculate I and E and so forth, or you remember the pi chart that'll help you through it. Now, this here is a I'm not sure what they call this. This is the combination of the voltage and the power equations, right?
Yeah.
And so you can see that power can involve square roots and squares, okay? So this gets a little more interesting here. Let's start with the simpler things first. If you look in the center, you see P, and then I, then E, and then R. So in the upper right, between 12 o'clock and 1 o'clock, you have E over R, and that's related to I in the middle. So we know that E is equal to IR, or that current is equal to E divided by R. Okay, so that's that equation. But I is also related to power and voltage. So between 1 o'clock and 2 o'clock, you see power divided by the voltage is equal to I, the current, or I think more commonly you might say power is equal to voltage times current.
Yeah.
Now the next one, yeah.
Hey, I just wanted to jump in because this circle diagram here is really pretty cool, but I do want to let everybody know you don't have to know everything that is on this diagram here. Truthfully, for your technician exam, the equations that you need to know are the ones with both the pi and the E over IR circle. If you know those two there, you're going to be fine. And the good news is I know going through all of these equations probably got pretty dry for folks after a while, but we just covered a bunch of questions on the, potential questions on the exam. So once again, and I hope everybody's comfortable with it, if you're comfortable with those formulas and using either the pi or the E over IR circle thing, you just covered a bunch of questions that are potentially on the exam. So.
Okay,
And,
thanks. Yeah.
Yeah,
So
and this thing here,
yeah, sorry, Joe, go ahead.
I was going to say, I had never seen this circle before, and I looked at it and I said, oh my goodness, what are they doing here? And then I looked at it for a while, and it is actually really handy. And also depicted on here are the color codes for the resistors. We talked about the resistors before with the color codes. We don't have to get big into that. But for everybody on the group, when you do get a little bit more comfortable with electronics and everything like that, you may want to revisit this circle because actually there is a lot of really cool information on it.
Yeah, it'd be a nice thing to hang on above your workbench if you have a workbench. You're building.
On that note, Nelson, have you ever seen this before?
I don't think so.
Yeah.
I do not recall it. I mean, it all makes sense, of course, but no, I don't think I've ever seen this actual diagram.
Yeah.
So, hey, Joe?
Yes, sir.
Can you use the middle of this like you said on the other two? Like if you cover the E, that would be P times I divided by R? Conversely, if you cover P, it would be E times R, and then I divided into that.
P times E Divided by, now I'm going to do the math for that. That is an
Yeah,
excellent question.
I think it's correct. Joe, if I could interject, I think the assumption is that things inside the circle are things you don't know.
Yeah.
So if you put your finger over I, you can calculate I by taking the voltage and dividing by R. Okay, between 12 o'clock and 1 o'clock. If you know the
Yeah.
voltage and you know R, you can calculate I in the circle. Okay. Same is
Yeah.
true for the next one. If you know power and you know voltage, you can calculate I.
Yeah.
And so on around the circle. Does that make sense?
Well, kind of.
I was just doing the mental math here, and it doesn't quite work out the way the others do. So for everybody, what I recommend, between now and when you take your exam, stay with those basic ones, the pi circle and the E over IR one. Those will answer the questions. Like I said, this diagram here, I looked at it for a while and I thought, wow, this is pretty cool, but I'm afraid there's so much on here it may lead you astray for your technician exam. But I'll tell you what, like I said, when you become more comfortable with electronic equations and electronics, you may want to revisit this, because I can at a glance look at it and say, you know what, there's a lot of good information on there. A heck of a lot more than you need for your technician exam, though. Okay, I believe that was the last slide. Are there any other questions on Ohm's law?